Hello everyone, I have this exciting idea that I want to share with you, provided you don't tell anyone about my idea, because I'm going to make lots of money from this idea. So you see, there's this light bulb here. It's connected to a coil. I have a magnet. I know that if I move this magnet in and out of the coil, the bulb is going to light up. Why? Because the coil experiences a changing flux linkage, which will result in an induced EMF and an induced current. Now, what if I make this magnet go in and out repeatedly forever? Maybe I'll put two magnets like this so that we got repelling poles and repelling poles at the other side, right? So once I get the magnet moving, it's going to bounce back here, it's going to bounce back there. I'm going to make sure that collisions are very, very elastic, so there's practically no loss of Ke. Now, do you see what's happening? I can light up this bulb forever. I have an endless supply of electricity. I've solved the energy crisis. I've solved the climate change. I've saved the world. I'm going to win the Nobel Prize for Physics. No, not only that, I'm also going to win the Nobel Peace Prize. Is that right? Yeah, of course not. And the reason is Lenz's law. Now, Lenz's law is not a mathematical law. There's no formula, no nothing. The Lenz's law is very specific to electromagnetic induction. So it's saying that if you have an induced EMF, the polarity of the induced EMF is always to oppose the cause of induction. Now, this sounds a bit abstract, so let's have a concrete example. So let's say I have a magnet here and it's approaching this coil. The magnet is producing a leftward flux, and so if it's approaching, this coil is experiencing an increasing leftward flux. So to oppose an increasing leftward flux, the coil must produce a rightward magnetic flux. So we know the direction of induced EMF will be this way. Induced currents will be flowing this way so as to produce a rightward magnetic flux. Now here comes the important bit. Do you notice that this coil is now behaving like a magnet with a north pole on the right? This means as this magnet approaches the coil, it will experience a rightward repelling force, which is going to slow down this magnet. Now, what about when this magnet is moving away from the coil? So the magnetic flux produced by this magnet is leftward. Since it's moving away, the coil is experiencing a decreasing leftward flux. To oppose a decreasing leftward flux, this coil must produce leftward flux, meaning the induced current will flow this way so as to produce a leftward flux. So this coil is now behaving like a magnet with a north pole on the left. And unlike poles attract, right? This means as this magnet is trying to move away from the coil is trying to attract it. The coil is trying to slow down the magnet so that the magnet doesn't leave the coil. Just for completeness sake, let's also consider what happens when the coil is making the return journey. Yeah? So now it's moving rightward, approaching the coil again. So it's a leftward magnetic flux that's becoming stronger and stronger because the magnet is approaching. To oppose an increasing flux, the coil must produce a magnetic flux that's in the opposite direction. See? The thumbs are pointing in opposite directions. So induced current will be this way, producing a flux that's this way, meaning the coil is behaving like a magnet with a south pole here. So the magnet is trying to come in and the coil is trying to repel it away. So again, there's a retardation force acting on the magnet. And when the magnet is trying to move away, the coil will experience a decreasing leftward flux. To oppose a decreasing flux, the coil must produce a flux that's in the same direction. See, the two thumbs are pointing in the same direction. So the induced current is going to be this way, producing a magnetic flux that's leftward. So the coil is behaving like a magnet with a south pole here. So as this magnet is trying to move away, this coil is trying to attract the magnet back. So again, there's a retardation force acting on the magnet. So do you realize now what is the problem with my invention? So whether the magnet is approaching the coil or leaving the coil, the induced EMF and the resulting induced current is always to produce a retardation force on the magnet. So every time when the bulb lights up, it's at the expense of the Ke of this magnet. So over time, the magnet will slow down, even if the collisions are elastic, totally elastic. In fact, when the magnet eventually comes to rest, the total electricity produced is exactly equals to the initial Ke of the magnet. So there goes my Nobel Prize, and it's all Lenz's fault. Now come to think of it, Lenz's law is a direct consequence of the principle of conservation of energy. If the induced EMF doesn't try to oppose the induction, we would have violated the principle of conservation of energy. Alright, that's all. Ta-ta!